we sort of went out into the stream of people and grabbed them and pulled them in and said, let's talk science. And a whole lot of them would go, ah! Mystical. You're coming in it. Okay, well, Scott's off. I'm Joanne Reed. I do education primarily, and I'm an author as well. So let's see. Hello, John. Why don't you just introduce yourself and say hello?
I'm John Doty. It says on my degree I'm a physicist. I've never considered that a limitation, but I am basically I'm a physical instrument designer. I design things that go into space.
You're an actual rocket scientist type.
Yeah, well, I don't actually do the rockets, but I do the stuff that you bolt on the top of them. That's kind of scary. You work for 10 years and then you bolt what you spent 10 years on to the top of a rocket.
I hope it works.
Good afternoon to you as well, Abby. How are you?
I'm doing fine. Since we're talking about what the degree actually says, my degree says I'm a zoologist. So I've got a doctorate in zoology. What I mostly teach these days is human anatomy and physiology, and I've done a bunch of research in physiology. And I have a sideline in talking about evolution and the gender binary and what biology has to say about these things.
Now you're into virology as well.
Yeah, more or less by default, because I teach my students about the sort of both the whys and wherefores of this disease, but also kind of the big whys, like, this thing evolved, right?
It changes, my goodness.
It changes right in front of us as we're watching it, and all of this kind of thing. So yes, the lessons keep changing as well. I'm actually about COVID-19 right now in the class that I'm teaching. It's a human anatomy and physiology class, but I kind of figured this is a teaching moment like no other.
Yes.
So I'm using it.
Are you back now, Scott?
Yes, can you hear me?
Yes.
Yeah, I had to join with my phone in order to get audio to work.
It's your big blank screen.
Yeah, it's complicated, but I'm here.
Okay.
There are two of you.
Right.
There's one
there are two of them.
that just has a name, and the other one has a picture and some
Right.
marble behind it.
Yeah. Yeah, apparently the screen capture software, OBS, cannot capture my microphone input at the same time Zoom is capturing the microphone input. So I had to join with my phone to get audio.
These computers, so naughty and so complex.
Yeah.
And it was just working the last time we did all this.
Well, I'm sitting at my desktop. I don't have it running on my laptop. I'm not downstairs.
Wow. So there's the problem.
Yeah.
It's a vertical problem.
Right.
So
Well,
what's up,
anyway,
Scott?
welcome to Sidewalk Science. As I was saying, we're supported by the American Youth Association and the local Prairie State Humanists. And we're here to talk science. So you all are welcome. The URL displayed there on the YouTube channel now enables you to type in a comment or question. And if you're feeling bold, you can actually use that link to join our Zoom meeting too. So without further ado, let's dive into some science topics.
Where would you like to start, Scott?
I'm sorry, What was that?
Where would you like to start?
How about what we were talking about just before I went live today? White dwarfs and some news that white dwarfs can contain remnants of their planets that have gotten smushed into them.
That sounds interesting.
Well,
So-
that sounds right, though, doesn't it?
Yeah, Joanne, John, go nuts.
I keep thinking about is one of these days, our sun is just going to become so huge that it's going to engulf all the inner planets. And so then it's going to get shrunk down to a mere thingy. And so we would be contained within that thingy. So I would suspect that a white dwarf would have exactly that, the remnants of the planets that it is gulped up sooner or later. But then again, I have no expertise in this matter at all. This is a layman's point of view. So I turn it over to people who actually know something like John.
Well, what we used to expect is that if there were any heavy elements in a white dwarf, that they would have long ago settled into the core of the white dwarf and we wouldn't see them. That was the basic idea, but now people are looking at spectra of white dwarfs and they find not very strong, but they find absorption lines due to various elements heavier than the carbon and oxygen that we think are the major constituents of these things. And the current notion is that this is stuff that has somehow reached the surface recently and therefore hasn't had time to settle into the core. But the other interesting thing is that we see that white dwarfs, we're now seeing that white dwarfs sometimes have planets around them, very close in. This was a big surprise. We did not think that the process of making a white dwarf would result in planet formation, because these planets are, of course, are much closer to the white dwarf than the original planets, if there were any, in the system that turned into a white dwarf, because
These would have been inside the body of the
they
star
would have
previously.
been inside the body of the star. But so yeah, we're learning stuff about what goes on when a white dwarf forms. And this is all cutting edge, and stay tuned because we'll continue to look at it and change our opinions about exactly what's gone on and make more observations and have more hypotheses and knock them down and build them up. And yeah, science, cutting edge. Good stuff.
It's called science. Yeah. What do we
Is-
know? Nothing. So we keep looking.
Is the ever pending James Webb telescope going to help us with white dwarf astronomy?
Probably not very much. I don't know of any particular thing that it's good at that would help this problem, but I'm not an expert on James Webb.
Yeah, it's infrared, right? Rather than visible.
Yes. And white dwarfs, well, they're very hot, and so they put out most of their energy in the visible and the ultraviolet rather than the infrared. So the infrared is not obviously the place to study them. Although if you're doing spectroscopy, you go where the lines are, whether the object is luminous down there or not.
Mm-hmm.
I don't know of any specific thing that it would be good at here. In the infrared, the spectroscopy is mainly about either if it's of nearby things, and you can only study white dwarfs if they're nearby. They're not very bright. If it's of nearby things in the infrared, you're looking at molecules. And white dwarfs are extremely hot, so they don't have molecules in their atmospheres.
So even though they're comprised of carbon and oxygen and hydrogen nuclei, those don't form molecules. So they're not made of water, for example.
They're not made of water.
Okay.
They're hot.
Too hot for molecules.
Yeah.
But I've heard some speculation that white dwarfs may have a crust of diamond.
Yeah, it inside the pressure may be so high that they can solidify, but you can't see that from the outside because there's an atmosphere. The metals that we're seeing in white dwarf spectra are from the photosphere, which is not at super high pressure.
So it's for our viewers, the photosphere is sort of a gaseous envelope around a star, or in this case, white dwarf. And it's the region that's hot enough, but rarefied enough that photons can be generated and escape to find our eyeballs or telescopes.
Yes. Below this photosphere, the object is opaque.
Right.
Above the photosphere, the object is transparent. And the actual transition is not a sharp one. And so the photosphere is a region. It's not like a surface. And it has different temperatures at different levels. And that is indeed why we see spectral lines, because what we're looking at when we look at the spectral lines in a star is we are looking at at different wavelengths. We are looking at different depths and therefore at different temperatures and therefore at different surface brightnesses. And so what we see when you take a spectroscope and you point it at the sun and you see the Fraunhofer lines, those dark lines are where the photosphere is a bit more opaque, and therefore what you're seeing is higher up in the photosphere. We sometimes call this outer layer where you are seeing the Fraunhofer lines, the chromosphere, because it's where the color, where the different colors behave differently. So if you see, for example, a sodium absorption line, the sodium is more opaque to radiation than at that specific wavelength than generally is true of the photosphere. And so you're seeing cooler sodium because it's where it becomes opaque is higher up in the atmosphere where it's cooler.
The old Fraunhofer lines.
Those are the Fraunhofer lines.
Mm-hmm.
And they were discovered in the 1800s, right?
Yes.
And that's the basis of atomic absorption spectroscopy. So there's a little chemistry thing.
The other interesting thing, of course, is before the Fraunhofer lines, nobody knew what the sun was made of.
No,
Newton had deduced that it had mass. We didn't know, but we didn't know anything else about it. And then Fraunhofer discovers these absorption lines, and they correspond to lines that you can see in the laboratory. And all of a sudden, it turns out, oh, gee, well, there's sodium in the sun. We know that because we see the same lines in the solar spectrum as we see when we stick a piece of sodium glass into a Bunsen burner.
beautiful yellow orange flame.
Yeah.
When was
In the sun, you see them in absorption, and in the flame, you see them in emission, but they're the same wavelengths.
But when were those lines figured out?
First, I don't know, 1830-ish, I think. Well, it's one of those things where it faded in gradually.
Mm-hmm.
You know, it was sort of the late 19th century when Annie Cannon was trying to classify all this stuff and didn't really understand. She understood that she was seeing elements, and she knew what the hydrogen lines were, she knew what the sodium lines were and all that. But she didn't
1814.
understand that the classification she was making had to do with the temperature of the photosphere. And so she named her classes A, B, C, D, E, F, G, and the actual temperature sequence that we now use, and for weird historical reasons, we quote it from high temperature to low temperature, is OBAFGKM.
Do you want to share the mnemonic associated with that?
Yeah, I've heard it.
O be a fine guy or girl. Kiss me. OBAFGKM.
Yep.
So when did we figure out what the sun was made of?
Again, it kind of faded in. It was, late 19th century, early 20th.
Okay.
Fraunhofer did his work, according to Wikipedia, in 1814.
Yeah. I mean, it took a long time for all of this stuff to become clear.
Yeah.
Oh, and there's this huge
one-
thing in the with the church and everything else about, well, it can't possibly be because the sun is so pure. And he's going, no, it's not. Really.
Know that. I did know that. That's interesting. No, I was actually asking in particular because one of the arguments that was had early on about evolution was it wasn't just what we would now call young earth creationists, who at the time were called basically people who believed the Bible, who said that evolution couldn't have taken place because there hadn't been enough time. If you believe that the earth is only 6,000 years old. But it turned out that Lord Kelvin wound up making a similar mistake because, of course, we didn't know about nuclear fusion at the time. And he actually shot down the idea that the sun was so hot because it was burning coal.
Yes.
But then he did have this idea, which is hard to explain, but that basically the heat came from the sun collapsing in on itself. But therefore, his calculations came up with a number of years old that the sun could be, which would not make evolution possible. And this was one of these cases where even Kelvin could get something wrong from time to time, and that was one of those instances.
Yeah, he didn't know about nuclear fusion. Nobody did. And the other thing is, it's one of the few examples in science where I know of where biologists prove physicists wrong.
Right.
Because the time required for evolution was much greater than the couple of million years that Lord Kelvin derived for the age of the sun based on simple thermodynamics.
Right. Exactly.
There were similar arguments about the Earth because we knew that the Earth was hot underneath and didn't know about radioactive decay heating the Earth. Interestingly, of course, Kelvin's mechanism is what ignites stars.
Uh-huh.
When they first contract out of cold gas, they get very hot, and that's what ignites the fusion reaction in the first place.
That's interesting. I didn't know that.
And another example is Jupiter, which in its current age is emitting several times as much energy as it is receiving from the sun, because it is still radiating away its heat of formation.
Uh-huh.
From billions of years ago.
From billions of years ago.
Wow.
Yeah, I've read when doing some research about this topic, I found that it's generally believed that about half of the Earth's latent or intrinsic heat comes from radioactive decay, and the other half is left over from its primordial collapse. All right, let's transition. Abby, do you have an update for us about virus and vaccine news?
Well, as I said, we are now, of course, seeing some pretty scary variants on the original virus, SARS-CoV-2. And as I have said, this is evolution in action happening right in front of us. And I'm going to add that this is also very sad from the standpoint that any evolutionary biologist and any population biologist can tell you that basically, well, first off, this was going to happen, but that you are more likely to get these kinds of variants when you have a larger population. It's basically arithmetic that, and I'm going to make up numbers here just to make our lives easy. But if you have, say, 1 in 1,000 viruses that undergoes a mutation, that's actually pretty conservative. But the point is, most of those mutations are not terribly interesting. Maybe they're worse for the virus and the virus dies out, or maybe they're kind of neutral. But every now and then, let's say maybe 1 in a million, you wind up with something that benefits the virus, that is to say, allows it to reproduce more, or that is in some way more damaging to humans. So you just do the simple math that if you have something like that happen with 1 in every million viruses, if you've got a small population of viruses, you aren't going to see very many mutations that are damaging to humans. But when you've got billions of viruses breeding all over the world, you're just more likely to wind up having these damaging variants show up.
So, Abby, do you think that some of these mutations are being drawn or influenced by selective pressure? Is the vaccine that we're distributing piecemeal to the human population having a noticeable effect on evolution of the virus, or is it just random mutation at this point?
I think it's kind of early days for the vaccine to be having an effect like that. So I'm going to say probably not. And what we hope for, obviously, is a vaccine that by and large keeps it from being spread about. If we get that, if we really have a pretty good solid vaccine campaign with pretty good vaccines, we can hope to, get the numbers of viruses down low enough that it more or less goes away of its own accord. Basically, you can starve them out if they can't find hosts. This is the whole point behind contact tracing, is that if you have somebody who is infected and you meet up, and you then telephone everybody who they've had contact with who might possibly have gotten the virus and be positive and tell them all to stay home, you're essentially starving that particular branch of the viral line out of existence. And what a vaccine campaign is going to hope to do is have that happen big time. And this is also, I'm going to say, the massive vaccine campaigns are the correct and proper use of the word or the phrase herd immunity, which has been bandied about far too much recently. I'm going to back up a little bit because someone recently suggested a very good way of talking about this, which has to do with another scourge of the human race called smallpox. And smallpox was around, and I'm going to talk now about European and Native American populations because they're the ones that I know about. But basically, smallpox was rampant in Europe for millennia, really. And European populations never developed herd immunity to smallpox. It did not happen. It was bad every time there was an outbreak. It was bad news, and it was fatal a lot of the time. And when it wasn't fatal, people got very sick, and very often they wound up with pockmarks all over their faces. And by the way, for those of you who read Romeo and Juliet in high school, that's where a pox on both your houses comes from. So anyway, smallpox was very bad, and it was around for a very long time, and Europeans never developed herd immunity to smallpox. This gives us a clue as to what is wrong with the herd immunity argument for COVID-19. I will add that when there was contact between European populations and Native American populations, this also gives us a little bit of an insight as to why COVID-19 has been so bad for us. Because European populations, although they did not achieve herd immunity, what they had achieved over the many years was a little bit of evolution towards some resistance to smallpox. And that's just basically because the people who were not resistant to smallpox tended to die. And very often not have children therefore, or very often, unfortunately, sometimes entire families died. Smallpox was really awful. So anyway, but the point is European populations over the millennia actually evolved a certain low level of resistance to smallpox. And when European populations came in contact with Native American populations, the Native American populations had no evolved resistance to smallpox, and it was even worse for Native American populations than it was for Europeans. That was in large part, that plus a lot of other European diseases, was a large part of what devastated Native American populations once contact took place. And there are a lot of follow-on consequences to that, which would be a good discussion for another day. But the point is, as I said, this is again a little bit of evolution lesson where you did wind up with an evolved resistance in the European population. You didn't in the Native American population. And circling back to COVID-19, COVID-19 was what became COVID-19 was originally diseases in pangolins and bats. It was coronavirus diseases in those animals. And it has been pointed out by me that they are fairly common diseases amongst these animals to the point where over the millennia, they have actually evolved a certain level of resistance to these things so that what is a very bad disease in humans is just kind of an annoyance. It's like a common cold, more or less.
So,
a pangolin or a bat. But then when it makes the jump into humans, we have none of this evolved resistance that the pangolins and the bats have, and that's why it's knocking us silly.
so one of the questions that comes to mind is that if there, insofar as there is such a thing as herd immunity that arises as a virus tears its way through a population, it takes generations. It's not something that happens in a year or 2 years. It takes generations for resistance to evolve.
Well, resistance and herd immunity are two very different things.
Okay.
But the resistance is something that can evolve. Herd immunity only comes about through mass vaccination.
Okay.
And that is why smallpox is not a problem for us now, because there were massive vaccine campaigns that took place that vaccinated every adult they could find, and then it became a standard childhood vaccination so that every generation coming along got vaccinated for smallpox in the US. I'm old enough to have a smallpox vaccination scar. Probably you guys are too, right? But there was a vaccination campaign that went all over the world and vaccinated every last person they could find to the point where we actually drove smallpox into extinction. It no longer exists, except in laboratories where we kept a few because we wanted to study them. But smallpox no longer exists in the wild, so we actually drove it extinct. But in general, the way that herd immunity works is that if you have enough people who are vaccinated, then what that does is, I'll back up a little bit. There will be some people who will still be susceptible to a disease despite our best efforts. Let's say they are transplant patients and they are on immunosuppressive drugs, for example, or they are undergoing chemotherapy. What they are hoping for is what's called herd immunity, which basically means the disease is not being passed around them. So basically, it is the fact that everybody else in the population around them does not have the disease that keeps them safe, because the disease can therefore not be passed to them.
So what about the notion?
Herd is keeping those few susceptible individuals relatively safe. That's the actual concept of herd immunity, and it works pretty well. And unfortunately, it stops working when people aren't vaccinated, when vaccination levels go down. There was a devastating case of this out in Washington State a few years ago, where there was a woman with breast cancer who wound up getting and dying of measles. And it is because vaccination rates were low enough for measles in the area where she lived that somebody somewhere in a doctor's waiting room or something had measles and wound up giving it to this woman with a suppressed immune system who died of it.
So what about the notion, which seems pretty malicious and horrid, that if a virus has a fatality rate of 2% or 10%, then eventually everybody will catch it, and the people who survive are immune to further infection? Is that a type of herd immunity?
Well, but you have the problem there that, you're not going to have everybody catching it because people move around. There's also the problem that you always have infants being born. And as I said, smallpox tried to give us herd immunities and it just never worked. So I really wouldn't count upon that. It's an interesting notion that does not seem to be borne out by the history of science. I'll just put it that way.
Great.
Well, my generation, we got chicken pox and we got measles and we got rubella and we got whooping cough. I mean, I had them all.
Mm-hmm.
And
the
older people had them too, but
And
you
polio.
keep bringing in new people and they're not immune.
Yep.
Don, did you have polio?
No.
Uh-huh.
Oh,
Yeah, we're very
but it was a terror in Western New York.
Mm-hmm.
It's scary.
When I was like 5 and 6, and I did have classmates who had it.
Wow. And we've come very close to wiping out polio, haven't we?
We've tried, but there are real problems with vaccine campaigns in places like Pakistan, where it is thought, sometimes with good reason, that people who are out there doing vaccinations may or may not, be working for be spies, basically. Sometimes, unfortunately, there are bad actors who impersonate vaccination campaigns. And sometimes perfectly innocent vaccination campaigns wind up getting, rounded up by one warring faction or another because they're under suspicion. So we keep trying to eradicate polio, but we have not yet succeeded on that one. And the problem, unfortunately, there is that, when you don't get rid of it, then it kind of breeds back. So it's been making a little bit of a comeback recently, which is not to say we have failed utterly. We still have a chance of eradicating it, but we've had some setbacks in that.
The other problem with polio is that the easiest vaccine to deliver is the live virus, is the attenuated virus vaccine. And sometimes that back mutates into a virulent form.
Oh, that's interesting. I didn't know that.
Yeah.
Yeah,
So,
you're right,
Abby-
Sir John, it was a scary time. I lost a classmate, and my younger brother lost a classmate, both to polio. And to a child, to lose a classmate to something like that, it's just so traumatic, and it was scary. I people who are around today can't believe how frightened we all were. And
Yeah.
the March of Dimes was the big thing. We all contributed, and it was just scary as hell.
So Abby, I wanted to talk to you about some of these mutations that are making fighting the virus more difficult, or potentially more difficult. How does that play into the science of the mRNA vaccines? Could we quickly spin up a new variant of the vaccine using mRNA technology that could fight these variants, or what's your insight in that?
That seems to be what people are saying. Now, the way that the mRNA vaccines work is, I think we talked about this last time, but that basically once the genome for SARS-CoV-2 was published, which happened back in January a year ago, once we had that, then basically the people who know these things were able to figure out which bit of that sequence coded for the spike proteins. And the spike proteins are sort of very characteristic of these coronaviruses. And so that then was the bit that was put into the mRNA vaccines. I should explain that the virus SARS-CoV-2 is an RNA virus. So that's the hereditary material it has anyway. So anyway, they take this tiny snippet of messenger RNA from the virus's genome, and that gets packaged in the case of the two vaccines that are being used in this country, Moderna and Pfizer. In both cases, they encapsulate it in basically a little bubble of a lipid. That is to say, their lipids are in the same chemical category as fats and oils. And it is able to deliver that messenger RNA into your cells. The cells then getting this little bit of RNA. I know I've said this before, but I'll repeat it. The central dogma in genetics is DNA makes RNA, RNA makes protein. So your cells get presented with a teensy bit of RNA and they make it into protein, and specifically the spike proteins. And then your immune system gets a good look at the spike proteins. And this is what enables your specific immune system, not the sort of general sentries that will just wipe out anything or try to attack anything that looks foreign, but your specific immune system that can make antibodies against a given disease. Your immune system gets a good look at these spike proteins, figures out how to make antibodies against it. And the idea then, which thus far has been borne out nicely, is that once you've got the idea of how to make those antibodies, when you are presented with an actual SARS-CoV-2 virus, you breathe one in or something like that, and it tries to invade your system, you have antibodies already primed and ready to take it down.
One of the analogies I've used to describe this in the past is a costume. Right, the vaccines that are based on RNA essentially present a costume to your immune system, and your immune system says, "Oh, I know that. That's Winston Churchill," and it recognizes the costume, so that when the real McCoy shows up, the costume has primed and programmed your immune system to react to that presented visage.
Right.
And it attacks it.
That's an interesting analogy, yes. And so, as I said, those two vaccines have been very effective. The question, we now have with the new variants is how much have the spike proteins changed? And apparently they've changed some. Or I should say, no, I won't say that. There is some evidence with the ones that appear to be more transmissible, more contagious, basically, that this might have something to do with how the spike proteins interact with the receptors on our cells. So we don't know, but I would say it's fairly hopeful that if the vaccines we have are less effective on the variants, and I'm not sure about that right now, there seems to be a pretty good promise for the idea that booster shots could be developed using the same technology. So I'm feeling reasonably good about that, but it's all happening right now. So the science is ongoing on all this.
It's very cutting edge. I saw something last week where there's some indication that the vaccines provoke a broader immune response to the spike protein than the actual disease does, so that they provoke the production of antibodies that bind to multiple sites on the spike protein.
Oh, well, that's good news.
And that is good news. That's good news because it's, a mutation in that affects one part of the spike protein may not affect another part. So that's good news.
Right.
The other thing that was in the Washington Post today is that the FDA is working on streamlined procedures for modified versions of the mRNA vaccines.
Good. That's excellent.
Have any of you been fortunate enough to get the vaccine yet?
Nope. My mother has.
Okay. I know here in the county I live in, the health department is making vaccines available to anybody 65 and older.
Mm-hmm. Yeah, that's the way it's working in a number of places. Not the way it's working where I live and where John lives in Massachusetts, where it has been kind of retained for people in long-term care facilities and for COVID-facing healthcare workers, which I think are actually pretty good priorities, but it has meant, unfortunately, that there are actually vaccines that are going unused right now, which I consider a real shame.
I think there's also an effort to make sure teachers get the vaccine so that they can do in-person classes. I don't know what that means for the students. But.
Well, I think that is a great idea simply because older people, we already have the science on that basically older people, particularly over about 60, do have less good reactions when they get COVID-19. So if you catch COVID-19, the outcomes are going to be worse if you are an older adult. So vaccinating teachers overall seems like a very good idea. It doesn't affect me one way or another. I'm teaching, but I'm teaching entirely online. So, I'm at the back of the line somewhere, and I just have to live with that.
I've been involved with a discussion on Facebook that one person has said, because of all this COVID and the lockdowns and everything else, there's no need for us to get influenza shots because, after all, it's like taking sunscreen at night. And I have suggested, of course, this is completely wrong, that this is a bad analogy, and that it's cheap, it's easy, and if you catch influenza at this point, there's no place for you to go. There's no hospital bed for you. You're going to die. Bye. So is there any element of truth to that?
Well, I mean, the more that we stay home and don't see other people and don't touch other people's stuff and don't breathe other people's air, we're far less likely to be catching all kinds of transmissible diseases. The flu is just one of them. So, there's that. But on the other hand, as you said, the hospitals are full right now. And if you can avoid going to a hospital, you'd really prefer to do that. You know, I mean, I got a flu shot. I'll put it that way.
I got my flu shot.
I got mine. Then
Yeah,
again, this is a highly intelligent group of people.
Well, yeah, I'm always cautious about, you know, drawing a line to say that intelligence is correlated with virtuous behavior. But
still,
but we're more likely to have learned or taken the opportunity to learn about the science.
yeah, we're old. We can do that.
Yeah. Speaking of intelligence and viruses, I'd like your opinion on the concept of memes, and that things like QAnon and some of the other wild conspiracies are like viruses in the universe of memes that are contagious and spread between people. And they seem to be spreading more rapidly in our era of lockdown.
Well, I mean, there is a certain decent analogy. You know, before we had real viruses to contend with in quite such a degree, you may recall that it used to be said that a post went viral. And that was because it wound up having some kind of exponential multiplication. And yeah, there's that similarity. It's a decent kind of, you know, slang to use for something that suddenly becomes very popular. You know, I think that studying how memes spread is kind of a fun thing to study, because social behavior is interesting. And I do think that there's something to the idea that during lockdown, when people are spending so much time on their computers, and the only way we can socialize is by going online, that things that you could see on the computer became much more powerful influences on us. So, you know, and that probably has to do with QAnon, but I mean, there have always been conspiracy theories. There's always been crazy stuff going on. And that certainly predates COVID-19. But I do wonder a little bit about perhaps the strength and the severity of responses during our time of isolation, because as I said, we are spending so much time on the computer that if you see something, you know, a dozen times, it starts becoming more important to you.
And you go searching for more.
What's that?
And you go searching for more. You look for confirmatory data rather than the overwhelming body of disconfirmatory data.
Right. And we've got the time now. You know, I think that goes for both conspiracies, but it may well be that is what really promoted all of the protests about racial injustice this summer, because people could watch this horrible video of George Floyd slowly dying, and you didn't just see it on the evening news for 10 seconds once and then it went away, but nonetheless it just, you know, came back at you time and time again, and it went on for 8 minutes and you saw it repeatedly, and there was really no denying what was going on. And I think that also, because we were spending so much time on our computers, there may have been an influence there. I mean, I think that this is something that may be a very interesting thing to be studied as time goes on, is, you know, what difference spending so much of our lives looking at screens had on various different social movements during this time. And, you know, I think there's going to be a lot of argument about that for years to come, because, you know, this is a peculiar time. And who knows, but I think it'll be worth studying.
Do any of the three of you know a social scientist that we might invite to one of our discussions to dig into some of these topics?
I'd have to think about it. It would be interesting.
Okay.
I would point out that this has happened before. The printing press kicked off several centuries of religious wars in Europe, as Martin Luther in particular spread his ideas, and other founders of various Protestant movements picked up those ideas and modified them and sent them around. And everything changed. And, the printing press, because it enabled mass communication on a scale that had never been possible before, really did change history.
That's a really interesting point. And I'm going to add to that because I looked into this when I was writing my most recent book, Darwin's Apostles. I looked into what amounted to the PR campaign that Darwin's apostles, Darwin's sort of scientist friends, mounted to get evolution accepted during Darwin's time. And they were aiming both at the scientific communities in England and the US, and also, and Europe, I should say, but also the general populations in England and the US. And one of the things that Thomas Huxley did was he was willing to use the social media of his day, which was newspapers. He also did a lot of public lectures in London, which was, a hub of activity at the time. But newspapers back in the day were the Wild West. I mean, there were, 2 editions a day of many newspapers. And, there were tabloids. There were things that, would embarrass tabloids today. There were all kinds of wild stuff. And a lot of the newspapers were, openly partisan and proud of it and this kind of thing. And they would, there would be letters to the editor that were as long as articles. Read, free content. And then there would be letters back, sometimes in the next edition, from somebody else saying why that letter writer was wrong. And there would be these slanging matches that would then drive circulation. And does this sound like Twitter? Yes. And this was all going on, in the 1850s and 60s and 70s. I will say 60s and 70s. But in any case, in England by way of newspapers, because newspapers really were the social media of their day, and they were used that way. And this was one where I give a lot of credit to Huxley, because he was willing to do social media. And most scientists were not and are not willing to go that route. And he did, and he was very effective at it. So, as John was saying, these things have happened before, but just with slightly different forms of media. But in some respects, because they are new and everybody's jumping on, they can have similar social effects.
So a couple of points about that. First, welcome, Ivan. I know you were able to join us a little later today. So
Hi, everyone.
We're talking about memes and conspiracy theories being analogous to viruses. And I'm wondering if there are lessons learned from the fight against Darwinism, or for Darwinism, as the case may be. And we've seen that particular fight go in waves. In the early 1900s, both presidential candidates, I think it was Teddy Roosevelt, and I can't remember his opponent, they both came out making statements in favor of Darwinian evolution. Teaching science is important to America. And yet here we are more than 100 years later, and one side of the political spectrum in America is far less likely to endorse the science of evolution. So the war against viral memes, incorrect scientific thinking, continues. And I wonder if we can learn lessons about the century and a half of struggle of Darwinian thinking. And the second point is I've been working my way through a book called A Lot of People Are Saying. And in that book, the authors say that Twitter is particularly well suited to conspiracy thinking because you're limited to 148 characters or whatever it is, and you cannot present an argument. You just present an assertion. And in fact, this is what this whole book is about, is that assertions have replaced arguments in our political dialogues. And you no longer need to support your claim either with putative contrary evidence or supporting evidence. You just have to make an assertion, and its validity is sort of measured by the number of people that like it and forward it.
I have said that Twitter is like the social media equivalent of the Monty Python Oscar Wilde sketch, where everything is a one-liner. But there is a lot of, the thing that surprised me, I think, is that I have been able to find a lot of really good explanations and arguments on Twitter. Like if you find scientists, often they are working on Twitter to explain their theory in simple form, especially when you look at things like epidemiology is one of the topics that I've been reading about, and causation. So it does exist, but yes, I mean, it does seem like a lot of Twitter is all about zingers, right? One-liners.
Did they link to a more expository format, or do they just reduce their ideas to one-liners?
You can have multiple Twitter messages where people will say, one of 12, and they'll just keep going for a while.
Yeah, it's a combination of the two. And the last one that I read was a Twitter thread, and the author had made graphics and posted multiple graphics with each one to explain, I think this might have been effectiveness of vaccines or something like that.
Cool.
So Joanne, you had a list of science topics. Is there any one in there two that you'd like to pick out?
I love the one about the U.S. Navy has patents on technology, it says, that will re-engineer the fabric of reality. And I love this claim. This fellow is claiming that he properly uses spin electromagnetic fields to contain a fusion reactor. And the U.S. Navy has patents on this. And they're going to then reformulate the entire United States Navy, and they're going to have fusion power. And experts theorize that a functioning fusion reactor could lead to cheap and ubiquitous energy. And I just had to laugh.
What is that, 50 years old?
Oh, this is, let's see, this was in what? Can't remember which article this was. Let me call it up.
But they've been saying that for 50 or 60 years.
Yes, but this is a new patent by the United States Navy. So
the article was paywall.
I have patents.
$3.
I have patents. You don't have to make anything work to get a patent. You just have to have an idea.
Really?
The idea doesn't have to make sense.
Just has to be original.
That kind of thing. That it was a patent was a physical entity, unlike a copyright or something like that.
Yeah, with a copyright, you have to have actually written something.
Yeah, but it could be anything. It could be a flight of fancy. Well, I've copyrighted my books, and they're fantasy. They're epic fantasies. So there's no reality to them. But this is a patent, and a patent at least has to have a basis in some kind of a structure.
No, it
I don't
doesn't.
think you can't.
No, it just has to
patent
be an idea. You know, you can patent fairy dust. You probably can't patent fairy dust because it's an old
Don't
idea.
you have to have a
but
working prototype?
You don't have to have a working prototype to patent something.
There was
Yeah, there's a big
My
patent
patents
lawsuit.
my patents are ideas that in fact never worked out, and I never actually managed to make a working prototype. But what you do is you file for a patent when you have the idea, because the patent goes to the first to file. Doesn't have anything to do with it, whether the idea will work or not.
Right.
interesting. Yeah, this actually, if I may kind of go off topic and talk about patents for a moment, this is one thing that actually came up, at this point, I'm going to say 20 years ago, something like that, where there's a real problem. And it all started with physiology, where basically a lot of work was done about industries that go 24/7, looking at the best way to do shift cycles. So, basically how to arrange shifts so that the people on the shifts are as healthy as possible, because there were some mines where you basically had people who were falling asleep on the job. And it turned out that it was because they were on a reverse rotating shift schedule, which is very, very bad for human sleep cycles. And so as a result, people wound up, they're very good in terms, they look fair, it turns out. But the problem is they are very, very bad for human sleep physiology. And as a result, as I said, you had people in mines who were falling asleep while they were working, which is a really bad thing to have happen. And so circadian physiology wound up getting a huge boost from industry at that point, and it became a real thing to study. And one of the things that came out of all of this was that we found out that of all the different things that might be the sort of driving force for the human circadian clock, this basically, we have cycles that go on sort of 24.5 to 25 hours. And it just this cycle keeps repeating itself. And every day we reset the clock a little bit to the 24 hours that we actually experience in the outside world. But it turns out that the thing that is most important to our sense of the 24-hour cycle of reality starting again is light. Light is the thing that tells our brains what time it is. It is not social cues, which was thought at one time. It is not eating. It is not all the other things that we associate with getting up in the morning or becoming stimulated or this kind of thing. The thing that actually sets us in, that resets our biological clock, our circadian clock, is bright light. Really bright light. And this can be used with some effect to treat jet lag. If you sort of apply bright light at the right time in somebody's circadian cycle, you can either move them forward a bit or hold them back a bit. And this has all been worked out rather nicely and tightly. But somebody got the bright idea of patenting bright light. Yeah, that's where I was going with this. And it's true. No, bright light for the purposes of what's called circadian shifting, basically treating jet lag.
Yeah.
But that can also go for what amounts to jet lag in shift workers, shift lag, if you're changing people's shifts around and all of that kind of thing. Or in research looking at these phenomena, that got patented. Bright light for circadian shifting, even to do research on it, that has been patented.
That reminds me of a news story I saw recently about a study showing that human sleep duration was correlated to the moon cycle. So during full moons, even people who habitually stayed inside with artificial lighting tended statistically speaking, there was a noticeable reduction in the amount of sleep that people got during a full moon compared to a new moon. And this was conducted recently, I think, in Portland and another city. And interesting correlation with the moon cycle. I know there's also a correlation between the moon cycle, or at least the length of the moon cycle, and human female menstrual period or menstrual cycle. And there's still not a good consensus, last I heard, about why that might be. But maybe it had to do something, with my own conjecture, with sleepless moonlit nights.
I know.
I've been using the bright light thing for years.
Oh yeah.
You know,
Oh, no,
when
and
I go to Japan, I get a window seat and I close the window when it's dark in Japan. And then when the sun comes up in Japan, I open the window and look out a lot.
oh sure. And I mean, I've been doing things like that for my own jet lag. And there was one time when I was doing research on what amounted to a visor that you could wear that shone bright light into your eyes. And but again, it helps to time it correctly.
It helps to time it correctly. The other trick is that I usually go a day early and arrange to go for a hike in the mountains or something like that.
Right.
That really helps.
That really helps a lot.
I do not. One problem I've had the last time I went to Japan, which was a few years ago, I took a 787, and they turned off my window remotely. The 787 doesn't have shutters on the windows; it has electrochromic glass.
Yeah. So, one of the things that I've read is that the cells in your eye that are light sensitive, that program your circadian rhythm, are not the same photosensitive cells that we use for visual light detection. It's a whole separate brain mechanism with different photoreceptor cells compared to vision. And so people that have some sleep disorders may have a problem in this wiring circuitry or the function of these light receptors that are not implicated in vision. And that's a topic of study for people looking at sleep disorders.
Ahead.
It was the pineal gland that was involved.
Oh, well, okay. What happens in the brain is that, well, first off, you need to understand that when I say bright light, I don't mean a reading light.
No.
One of the things that photographers all know is that even a brightly lit interior room that is, fine for reading and functioning in and this kind of thing is basically a cave compared to outdoor light. That's why you always, back when we didn't have cell phone cameras that were so darn smart, you always had to have a flash when you were taking interior pictures. It's because indoor light is nowhere near as bright as sunlight. I mean, multiply it by 10 or 100, this kind of thing. It's much brighter outdoors. And our eyes are really good at accommodating to all these different levels of light so that we can function. We can read indoors with just a decent light. We can do all kinds of things. And then we go outside on a bright day and we can do things outside as well. Our brains are not as good at accommodating. And so the level of light that actually affects our circadian cycles is actually much brighter than your average indoor light. And this is why people who suffer from seasonal affective disorder need to sit in front of a really bright light bank or go outside or something like that. But the part of the brain that actually responds to light and the part of the brain that actually sets our circadian rhythm, the part of our brain that keeps the circadian rhythm going and that can be reset by light is a part called the suprachiasmatic nucleus. It's SCN to its friends.
That sounds like a superhero name.
It does.
Chiasmatic nucleus, right, right. And it is not far from your pituitary gland. And there may be some association there, I'm not sure. The brain is a very weird place anyway. But as I said, I know that the pineal gland has some vague connection with it as well, but the one that really keeps our circadian rhythms going, as I said, is this little bit called the suprachiasmatic nucleus.
Is that in the brainstem, the ancient brain?
No, it is exactly above where the optic nerves enter your brain. If you actually want to take apart the word, which I love doing in physiology, supra means above. Chiasma refers to the optic chiasma. Each of your eyes has an optic nerve coming from it. Those optic nerves head towards your brain, but they do not go directly into your brain. They actually cross first and swap some fibers around, which is why each cerebral hemisphere gets information from both eyes. There's a little bit of swapping of fibers that goes on. So as I said, these two optic nerves coming from your eyes cross, and then it's the bits on the end here that actually enter your brain. This crossing that happens right just below the brain is the optic chiasma. So you put the words together, and the suprachiasmatic nucleus is that little bit of a brain that's
Above it.
the brain that's just above the optic chiasma. So
The
kind
pho-
of the bottom of the brain, kind of sort of back here behind the eyes, kind of sort of there, smack in the middle.
So the name of the cells that are photosensitive but aren't rods and cones are, I just looked it up, intrinsically photosensitive retinal ganglion cells.
Cool. Did not know that. I mean, I did know about ganglion cells, but I didn't know what they were for.
Yeah, and the article I'm looking at talks about links between specifically those cells and circadian clock. And I thought the circadian clock, because it was common to so many organisms, had components in the brainstem.
Well, it's all back here somewhere in the occipital region, isn't it?
Yeah.
So the that word it has to do with eyes, right? Occipital.
I know.
Oh, by the way, Abby, I would, while there's a little silence, I would tell you that it's the factor between bright sunlight illumination and interior illumination is more like a factor of 1,000. It's like 10 stops to a photographer.
Yeah, I have actually both studied it myself and looked at the papers, but I was speaking casually. But yeah, it's a huge difference.
Well, I'm just an old photographer. 10 stops is a lot.
Any
1,000, John?
has done photography back before cameras were quite so smart knows about all of that.
I think I would get impossibly nostalgic if you gave me a whiff of hydroquinone.
Your dark room.
You lost me on that.
It's a common developer ingredient.
Ah, okay.
I know Ivan does a lot of photography too, but you're all digital these days, right?
That's right. I was into photography when I was a kid, and then picked it up again when digital cameras started to get competitive. And yeah, we talk in photography. We talk a lot about dynamic range, which is the difference in the if you take one frame, how much of the image can be correctly exposed. If you had a gradient from very dark to very bright, how much of that would you have data that you could see? Because when it's very, very bright, it will just be overexposed. And because it's a digital camera, there's a brightness number associated with every pixel. So when it's overexposed, if that number goes up to, let's say, 65536, well, above a certain point, everything is 65536, and you're not seeing anything there except pure white.
Yeah.
And at the low end, once you get too low, even if it's like 0 and 1, if it gets all the way down there, then you're really not going to see any detail down there, and there's going to be noise anyway. So the
resolution to discriminate brightness levels improves as you go higher with that number because of the way binary arithmetic works. So one of the things that digital photography recommends as a pro tip is called exposed to the right. So you want a very slight overexposure without blowing out the highlights. And that gives you more dynamic range to play with when you're doing your photo process.
Yeah, it's not just the digitization, it's the shot noise and the photons too.
That's right. You've built all kinds of photon.
I have done this.
Sensors.
Yeah. I was doing I was working on digital photography for astronomy in 1974.
I recently purchased a new camera just for my telescopes, and it's got a very sensitive new Sony detector, and it's just amazing the technology for